All right, let's go ahead and try 13.5. This will be my second time going through this video. I just recorded the whole thing and then it didn't record. So let's go ahead and try this again. So I have a lot of stuff already written out. So let's start with the binormal vector and introducing it. The binormal vector of a curve in space is just going to be the tangent vector crossed with the unit normal vector. So our unit tangent crossed with our unit normal. And when we do that, we're going to get a third vector that is perpendicular to both of them and is therefore also normal to our curve. Therefore, we call it the binormal vector. And that's what we get there. It's very useful in calculating the paths and what's happening with the particle here as we move along. So let's take a look at this. There you go. There it is showing it. You see the tangent vector to the curve there, tangent, and you see the normal vector. And then if you cross them, you get that B vector there, right there. Okay? And what we can use this for is, one, we can use it to start looking, well, in a minute here. First, we're going to look at the acceleration here. First, we can take and find the velocity vector by doing the rate of change of the radial vector, so dr dt. And then we can use the chain rule to turn dr dt into dr ds times ds dt, where that ds dt is the speed. And what we end up with in here is the unit tangent times our speed, which is the magnitude of the velocity vector. And that should make sense because that's what velocity is. It's a speed in the direction that is pointed. The unit tangent points in the direction it's going, and then the speed tells us how quickly it's going in that direction. So just those two multiplied together gives us our velocity vector. So that's what vectors are, right? They're a magnitude and a direction. So the unit tangent is giving us our direction, and the speed is giving us our magnitude. We then can take that and use that to find the acceleration vector, which is dv dt, which can become the derivative of t times ds, right? So the derivative of this version of it right there, which means we can then apply this through and do the product rule. So we do the derivative of ds dt times t, that's this first one, and then we do the derivative of t, which is that, times ds dt. So that's our product rule right there. And on the left side, the second derivative of s with respect to time times the unit tangent, we can leave that alone. But on the right-hand side, we can actually get this into terms of it being in the unit normal direction. So dt dt becomes dt ds ds dt right there. And we can replace dt ds with kappa times the normal vector, because that's what that one equaled to. And then it's times ds dt, which is again just our speed, our speed right there. And so what we end up with then is kappa times the normal vector. That means this is just times ds dt. We can lump those together right here. And so what we end up with is two different components. We have all the part that's tangent to it, all of the acceleration that's tangent, and then we have all of it that is perpendicular. So we have the tangent and the perpendicular, or the normal, projections of the acceleration, which means we can just look at these parts I underlined in red. This is the tangential component, and this is the normal component for the acceleration. All right, and so we can come over here and actually break apart our acceleration vector into its tangent projection and normal projection, where the components of each are defined by what we just figured out on the other side. The tangential component is the second derivative of our arc length right there, our little speed there, and then that is just the first derivative of the speed. So a nice easy way to calculate the tangential component of the acceleration. And then from there, we can look over here, we had kappa times ds dt. That becomes just kappa times v squared. So a way you could calculate that, you'd have to calculate the curvature first, kappa, before you did that. So here we can see all of those vectors on this nice diagram, where we have the acceleration going off in this direction, and then we have this component here that is tangent to it, which has a length of d2s dt squared, and then we have this component here that has a length of v squared over rho, or kappa times v squared. Okay, and so we have those two things right there for finding the components of that acceleration. Here is a nice little formula. This just comes from the Pythagorean theorem. The tangential and the normal are orthogonal, and they are the components of A, so therefore we can say that the magnitude of A squared is equal to the tangential squared plus, or the tangential component squared plus the normal component squared, and then take one step and subtract the tangential component from both sides. And then what we have there is a typically easier method for calculating the normal component, where you don't have to find the curvature or anything like that. So once you find the tangential component, square it, take it away from the acceleration, the magnitude of the acceleration squared, and square root it. Typically an easier way. Here's an example of that being done. If you go to page 793 in your book, you can actually find this example there to go look through and see how it works. I'm not going to go over here because I don't have a lot of room and I don't have a lot of space here to do it. So make sure you go look at that page 793 and walk through as they do that example for you. But essentially what they do is they use this right here to calculate the tangential component, and then they take that and plug it into this to find the normal component, all right, without ever having to find t and n. Okay, next here, I had written this all out already, so let me erase this here. So what we're doing is, how does dB ds behave in relation to the tangent, the normal, and the binormal? Well, dB ds is going to equal d times t cross n, because that's what b is, right? b equals t cross n. And then we can apply the product rule there, and we have dt ds crossed with n and t crossed with dn ds. Well, if you remember, n is equal to 1 over kappa times dt ds. That means that n is parallel to dt ds, and therefore this whole part right there, that term is 0. It goes to 0. So what we're left with is dB ds equals t cross dn ds. Well, if you think about this, since it's the cross product of t and dn ds, that means dB ds has to be perpendicular or orthogonal to the unit tangent, right? This must be true because it has to, because when you take the cross product of two vectors, the third vector is perpendicular to both of them. And so dB ds is orthogonal to t. And we already know that since b is a constant length vector, then that dB ds is also orthogonal to b. And therefore, what is orthogonal to both t and b? Well, that's n. Therefore, dB ds is parallel to the normal vector. From that, we can come down here and say dB ds is then just some scaled version of the normal vector, and the convention is to throw that negative sign on there. Doesn't technically have to be there, but it's convention, it's what everything does. If you then take and dot both sides with that unit normal, dot, dot, what you get on the right-hand side is n dot n, that's just 1, all right? It's just a unit vector dotted with itself, so it has 1, like 1 squared. And then what you end up with is just tau by itself. So put tau on the left side, put the negative sign on the other side, and we've got our equation for what tau is. And we can actually go ahead and give this a name, and we're going to call this the torsion function. What this does is tells us how much this is twisting. So if you think about like an airplane. As an airplane flies along, if it turns, it doesn't just turn straight, it also tilts, right? The wings will tilt. So if it's turning left, that left wing will go down and that right wing will go up. So if we're looking like at an airplane, right, from behind, this is the wing, here's the fuselage, here's the other wing, right, here's the tail. It's flying away from us. As it turns, if it goes to like fly off and turn to the left, what's it going to do? It's going to, as it flies off and turns, these wings, they're going to tilt, right? It's going to rotate as it turns. So the wings will tilt like this. So there's a twisting to it. And we have the same sort of things with these particle motions, and the amount that it actually twists as it goes around the curve, that twisting, is that torsion. So as this goes, it's going to twist like that. All right, and we call that our torsion, like a plane turning as it tilts. Or if you're riding a bike and you go to turn a corner, you lean into the corner that you're turning. All right, so that sort of stuff happens. And there is that torsion that is negative dB ds dotted with n. All right, here is a nice little picture here that shows you some of the names for some of the planes and the direction that these things are pointed in. So our unit tangent, our principal normal, our binormal. And then we have the normal plane between the two normal vectors, the rectifying plane, and the oscillating plane. So if you're, maybe a good idea to be familiar with those names. Here we've got just another picture as it goes around, as our arc length increases as we move along the curve. You can see that these things would turn and twist, and so you might get up here where the normal is like this and the tangent is like this, and this is now tilted over this way or something as it goes. It's not just necessarily going to stay like it was, and so these things would be rotating and twisting as we went through it. And you can see the planes that they're in. Those planes would also then rotate and twist and change angles and stuff. So that's pretty much it for this section except for this page. This page gives you a nice breakdown of all of these different vectors we have come up with for moving through these, the unit tangent, and how to calculate them, even some nice easy ways like for calculating the curvature right here, nice little way to calculate it. Also here for the, right here for the torsion, there's a way you can calculate it there that's usually simpler. Now, what do those dot means? Well, every time you put a dot above something, by convention, that means you're taking a time derivative of it. So one dot above it means you're taking the first time derivative of it, like what I did right here. And 2 dots would be the second time derivative, and then like 3 dots down here would be the third time derivative, and so on and so forth. So you're essentially taking like the velocity components, the acceleration components, and then the rate of change of the acceleration components called the jerk components. So the rate of change of acceleration is called jerk, and that's what those components would be. And then down here is just v cross a magnitude squared. So usually a kind of simpler way to piece that all together and calculate the torsion. Then we have the tangential and normal scalar components right there. And so you can see those where they add up, you sum them in the direction of the tangent and normal vectors to get the acceleration. And then of course the easy ways for calculating them that we saw on the previous page. So I think you'll probably have something like this to use on the test, but I'm gonna have to look through it again and make sure. So, remind me to do that. Here is an example I want you to work on. Basically find the curvature and torsion and do it using what's on this page. So find the curvature using that and find the torsion using this and try and do it. So you need to find V, you need to find A, and you need to find those time derivatives, which you should get while you're doing V and A, right? So go ahead and try finding those things. So use that, take your time derivatives, you'll get the time derivatives of the components, and they're your components to make up that matrix that you need to then take the determinant of, right? So it's the determinant of the matrix of all the time of the 3 different time derivatives of your vectors. Okay, so go ahead and do that, and I'm pretty sure, yep, that's the end of this section. So next video will be on the next section, obviously, and I hope this made sense, and I will talk to you later. Thanks for listening.